Okay, hello everyone. We are very glad to have you here for this joint meetup between Bucharest and Paris. And today I would like first to start quickly with our code of conduct. We want to have a space dedicated to providing a harassment-free experience for everyone. You can read the slide, but basically the idea is quite simple. It's just be nice to each other. And if you feel insulted, please do not overreact and just try to understand what the other person meant. We also have a version for the online code of conduct. Please mute your microphone when you are not speaking, so we don't have interferences. And if the moderator asks you to speak, please unmute yourself, of course. You can ask us a question either in the chat or through speaking, just by raising your hand. And if you get disconnected, which can happen, just calmly reconnect. We'll just keep an eye in the waiting room so we can accept you again. So what is WiMLDS? It stands for Women in Machine Learning and Data Science. And the mission of WiMLDS is to support and promote women and gender minorities who are practicing, studying, or are interested in machine learning and data science. To do this, we organize that kind of meetup where we ask some women to share their experience and their technical knowledge so we can all benefit from it. WiMLDS is a global organization with quite plenty of members worldwide, plenty of chapters too, new chapters every month. So if you just happen to be here without being in Bucharest or Paris, it's super cool, and don't hesitate to build your own chapter now or at the end of the pandemic, whenever you want. We'll be very happy to welcome you all over the world. Tonight's agenda, so we had, well, you see, we had this little introduction by WiMLDS Paris, and then we have the introduction by WiMLDS Bucharest, and then we have these three technical talks. First is Rapid Erase the Waiting Hassle by Andrada Olteanu, who is a data scientist at Endava. She'll present herself. As the second talk is Solutions for Running R on AWS Lambda by Anna Maria Niculescu. And the third one is Data Science for Financial Fraud Detection by Denisa Banulescu. And we are very happy to have these three amazing persons presenting here tonight. So we'll see what they have to learn to us, to teach to us, sorry. WiMLDS Paris, just in a couple of numbers, it was funded already 4 years ago, and we are very happy to be the third largest chapter in the world. We have a team of 4. We are a team of 4. From the left to the right, we have Chloe, you have myself, Caroline, and Natalie. And we have also plenty of volunteers helping us every day to plenty of other stuff. For WiMLDS Bucharest, I'm just letting you present yourself. I'm just letting you share.
Yeah, thank you. Yes. Hi, everybody. We are excited to benefit from one of the only perks of this pandemic, which is the possibility of having these joint meetings all over the world. The Bucharest chapter of Women in Machine Learning and Data Science is one of the newest ones. We've started in November last year, and we are happy that our fourth meetup is this one, and it is special. We are 6 women brought together by our passion for data and modern statistical methods. So far, we are a little over 150 members on Meetup. We are highly active on Facebook, since it's quite popular in Romania, but you can also find us on LinkedIn, and you can watch our recorded meetups on YouTube. You can help us grow our chapter by using our hashtag and spreading the word about us on social media. You can join us as a speaker, participant, or a member for our community. You can propose some topics or some speakers. And actually, we would be delighted if you could fill out the feedback form for a better organizing workflow in the future. Yeah, that's kind of all for my part, but I have to thank you again for this opportunity to learn from experience as a chapter, a big chapter. So yeah, kind of that's all. And should I pass to speak about Andrada, right?
Yeah, please.
Andrada, you can, if you want to share your screen. Our first speaker is Andrada Olteanu. She's a data scientist at Endava and a global ambassador at HP NVIDIA. I hope it's the right way to say it.
HP NVIDIA, yes.
She recently became a Kaggle notebook grandmaster, so I have to personally congratulate her because I didn't have the opportunity so far. She has a master in data science at Queen's University in Belfast. Today she will show us how to work with bigger data, pre-process faster, do more experience with our models, well, in less time, but writing kind of the same code. Let's see how can we apply the rapids. Let's hope that's how it's the correct way to say technology in, well, everyday workflow and make it fast.
Okay, so hello everybody. My name is Andrada. I'm super excited to be talking to you today. I don't know. So first of all, is everybody seeing my screen all right? Yes, no, maybe?
Yeah, I can see it.
Okay. I don't know how to make this thing disappear, so I think we shall let that stay for a bit. Maybe it will. I don't know. Yeah, so today I'm going to be talking to you about rapids. What is it actually, rapids? How can you use it? Why should you use it? Because I remember the first time I heard about it, I think last September, I was a little bit overwhelmed, and just by entering into the site, you don't really know from where to start. So hopefully today I'm going to be able to share some insights, some tips, and how can you benefit from this amazing tool. Okay, so first of all, what is Rapids? So Rapids is a suite of open source software libraries, and it was and it's still developed by the NVIDIA team. So NVIDIA created this super amazing, super smart team to work on Rapids, which basically, so when you're doing data science, usually if you're using Pandas, NumPy, Matplotlib, Seaborn, NLTK for natural language processing, anything of the sort, you usually are using libraries that are built on and use CPU. If you want to be able to tackle and also use maybe some sort of GPU that you have, whether on your local machine or on cloud, by using these libraries by default, it won't help you. So what Rapids did, and I'm going to explain it further as we go, is they've developed this suite of libraries that execute end-to-end data science and analytics pipelines, meaning that you can do anything from exploratory data analysis, pre-processing, to actual training a machine learning model, which are entirely on GPUs. So you can access easily as we're going to see, and quickly the GPU resource that you may have on your workstation or on cloud. They are working all the time, and they are releasing a new version every 6 weeks. And now I'm saying this here because in my opinion, so this is super important just because I remember the first time I used Rapids, I encountered some issues with the code, meaning that there weren't some implementations that I could have used and benefited from. But 2 months later, sometime when I wanted to reuse that thing, it was working properly. So they are implementing new features and new functions every 6 weeks, so you can benefit from this development all the time. So just keep an eye on the versioning, and if you have some issues at some point, there's a big chance that they are going to develop it in the near future. Okay, so why should we, I'm super annoyed about this. So why should you use GPU instead of CPU? And the very short version, very short answer is that because it's super fast. So you can see here a graph where we can have, like, let's call them 3 experiments. We have the data loading, some feature engineering, data conversion in blue, and in yellow machine learning training. So all these 3 are steps or processes in a data science pipeline. And you can see the comparison between, for example, 20 CPU nodes and how long does it take for this pipeline to run rather than on GPU. So this comparison is between 20 CPU nodes, 30, 50, 100 versus NVIDIA DGX GPU. This is how it's called. This is actually, it might not be fair just because it's a super powerful NVIDIA GPU, but nevertheless, it's extremely, extremely fast, and it can help you in your data science process very, very well. Now, why GPUs are so magic? Because this is not really a fairy tale here. So the difference between CPU and GPU stays at the foundation, or how they are actually created. And without getting too technical here, just because I don't like to get too technical, I am not very familiar with this part, but CPUs are created to have less cores. So they have usually between 4, 6, 9 cores, just a few cores that can perform only one task per job. And usually their calculation is very, very simple. It's just subtracting or adding values. These are very simple calculations that a computer can make. Whereas when we are talking about GPU, fundamentally, it is built different than a CPU. And this is why it performs much better in a data science pipeline. It usually has, so it has many, many more cores. It can perform multiple tasks per job. And it's extremely specialized, and this is what it does best, to do matrix calculation. If you remember, whenever you are doing, for example, and this is especially applicable in computer vision, when we are working with images, which are very, very big matrices, but in a machine learning pipeline, for example, such as decision trees or random forest, there are lots of matrices calculation involved behind. And this is why a GPU is so much faster, just because it's designed differently and tackles these data science, I wouldn't say problems, but algorithms differently and much more efficient. So going back to that analogy that I said, that I made earlier between CPU libraries and GPU libraries. Here we have 3 libraries that are very, very frequently used that are fundamentally created on CPU. So we have Pandas, which is created on CPU, and it's for data frame kind of preprocessing and managing. We have NumPy, and then we have scikit-learn. Now, to take for example, just a very basic function, let's say pd.readCSV, which just, you call it and you read a CSV file into your Jupyter notebook, for example. To take this very basic function and convert it to use GPU, it's going to take you a long amount of time, just because it's extremely hard to take the code that stays behind that basic function and to convert it to use GPU, because by default, it won't use GPU. So what the people from Rapids did was that they took these functions that are very fundamental and that are used every single day by data scientists and converted them from CPU to GPU. Why I'm saying this is because, and this is absolutely amazing that they did that. They tried, and I think around 95% of the functions converted from pandas to CUDF. This is the brother, the GPU brother. NumPy converted to CuPy, and scikit-learn to CUML. So these three brother functions, or libraries, I'm sorry, out of these are extremely similar, 95% similar, meaning that you don't have to learn to use these libraries. If you know how to use pandas and functions in pandas, it's a very, very high chance that you will be able to fare with CUDF very easily. And I'm going to show you a little bit of an example later, but just imagine by just saying import pandas and then saying pd.readCSV, you can very well say import CUDF and then CUDF.readCSV, and it works exactly the same. However, you are using that GPU resource. I talked a lot about GPUs, and they are absolutely amazing, and they are like the dragons of data science. However, GPU doesn't replace CPU, but it is a very good tool that you can use in some cases, a lot of cases, when you're doing data science. And this is because with CPU, as I said, it's much slower. So here you have a very, very cool example where you get home, get to work at 9, and then you are starting to configure a data science pipeline. So you're just hard coding. And then you kind of let your data run through that pipeline. And it takes a long time. You get a coffee and you get another coffee. And then you see that, oh, there's a bug here. Oh my God, I need to debug this and I need to make it run again. So you restart here, you switch to decaf just because you can't take it anymore. It's too much, maybe some water. And then you find some unexpected null values here that you had in the data, but it kind of, you just didn't observe them when you started at 9, and then you restart again and so on. So you can see here in blue, it's a lot of waiting involved, a lot of waiting that can be used much more efficiently. Whereas if you're using GPUs, you get here at 9, it takes a little bit longer, but not as much to create that pipeline. And then you start running, so taking the data through the pipeline. Oh, you need to fine tune again, fine tuning again. And then you can actually, at the second part of the day, start to actually train the model and hyperparameter tune and so on. So as you can see, this fastness makes everything, so it's not only you being much more productive and not only at work, I'm talking here in your own projects, in your own research or anything, but it's also extremely helpful into creating better models in less time, or even parallelizing your pipelines so you can try multiple experiments in the same amount of time. So it's absolutely amazing. And you can use the GPUs in all sorts of cases, especially in big data. during machine learning, as we saw earlier, and as I said, in image processing or anything regarding computer vision. I didn't know whether or not I should put this in here, but I am going to go pretty fast through this because I don't want to bore you to death. However, Rapids is absolutely amazing, but if you want to use it on your local workstation, it's gonna take a little bit of a headache. First of all, as I said, it's developed by NVIDIA and you'll need an NVIDIA GPU Pascal or greater. And another thing that's usually people are frowning at being like, oh, I'm not trying this, is because it needs Ubuntu. I've read a lot, and as I've seen, data scientists are starting to move towards Ubuntu rather than Windows. However, Windows is still like default and it's super easy and everybody is used to it. So it might take a little bit of willpower to move from Windows to Ubuntu, which I totally understand. I didn't want to use Ubuntu at first when I first started using Rapids. And then you'll need to install some prerequisites that are going to take a little bit, the NVIDIA Container Toolkit, and then some CUDA and NVIDIA drivers, preferably the latest version. Now, if you don't want to part ways from Windows and you still are clinging on it, before these prerequisites, you'll need to install YSL2, which by default is horrible, just because I'm telling the truth here. So I'm being honest with you. It will take a lot of updates on your Windows, and then I did actually, I left it here. I did a tutorial on how to install Rapids on your Windows machine. However, I remember at the end, it wasn't working as properly as it did after I switched to Ubuntu. So it's a little bit of a process, but if you want to do it, just equip with a lot of time, I would say. That's the only thing. And then they have on the side for Jupyter notebooks, for example, to use Rapids in your Jupyter notebook, you just select here some specifications. You are using the Docker, you want the stable release, you want all packaging, the latest Ubuntu version, the latest Python version, your CUDA version that you installed earlier, and then you just run these 2 lines of code, and then everything is going to be fine. But again, it's going to take a lot of time. And who has that time? And this is why I would highly recommend you, because Rapids is absolutely amazing. And I wouldn't not use it just because it's such a headache to install it on your local workstation. So you can use anytime Kaggle or Collab. I usually use Kaggle because I'm more familiar, I like it better, but you can use Collab as well. And in the Kaggle environment, for example, all you have to do is just open a Kaggle notebook, which works like a Jupyter notebook normally. You open the GPU, which is just a button there, and then you say import CUDF or import CuPy or whatever, and then you're good to go. Everything is running, everything is smooth, and you will be able to start your work. So before committing to installing on your local workstation and stopping on the way, I would highly recommend to do that instead. Documentation, so there's a lot of documentation there from Rapids, not as much on Stack Overflow, for example, as you'd see for Pandas, just because, for example, Pandas have been here a long time. But I've seen, especially in the last month, more and more people starting to use Rapids. Therefore, more documentation, especially on Stack Overflow. So if you are finding yourself in a little bit of an issue, an error or something, just go ahead, Google it, because, and even as time passes, there will be more and more people that might have your issue as well, and you will be able to solve it. Okay, so because this has been a lot of talking, and I know I know it's hard to comprehend only from theory. Sometimes, at least me, I need a little bit of an example, a practical example. I wanted to show you just how different sklearn and COML are faring in just training a little model. This is a notebook I've created on answer correctness competition on Kaggle a few months ago. If you want to get deeper and to see an actual example on how to use rapids, I recommend you check. I'm not going to go through the entire notebook. I'm not going to go through any of the notebook actually. But if you want to get a little bit a grasp of what rapids really does, I highly recommend. This competition had more than 100 million rows. So in this competition, rapids wasn't actually optional, it was very mandatory, because you weren't able to do anything with pandas just because it was such a big tabular data set. But what I wanted to show you here is just how easy it is to use rapids in a Kaggle notebook and how fast it is. So here, for example, I imported just CUDF, which is the brother of pandas again, and then CuPy, which is the brother of NumPy. Then I wanted to look a little bit of, just to see, to check the environment to see that everything is fine. I have one worker, we have almost 14 gigabytes of memory. And then I usually call NVIDIA SMI to check the environment. We can see the driver is the latest one for 5051 and CUDA version 11.0. And then the Kaggle notebooks use the Tesla P100, which is super powerful. Like it gets the job done. It's not the insanest GPU, but it's extremely good and it usually gets the job done. And here I wanted to give an example of a comparison between sklearn and COML. So here I just import the libraries, and as you can see, you import, so from sklearn.ensemble, I import the random forest classifier. Same thing from COML.ensemble, import the random forest classifier. Also from metrics, import accuracy score, which is super fast. It's much faster than the one from sklearn. So this is just how you are used to by using sklearn. Here I've created some fake data just to have something to work with. And here I've just split it into training and into our feature and our target variable. And here is the CPU data, so using sklearn. And here is the GPU data from using COML. And we can see here we have around 33,000 observations and around 400 features. So it's quite a big data. It's not big data, but it's quite a proper amount, I would say. Okay, and here is the example. So by using sklearn, we are creating a model, and then we are just fitting it like we normally would, and then we would evaluate it. And you can see here the training times takes around 6 minutes. So for 33,000 observations and 400 features, you expect to have around 6 minutes of training by using sklearn. And then I did the exact same thing using COML. So again, exactly the same model. I fit it and then I evaluate it. And it takes 20 seconds to run. So the difference is huge, 20 seconds versus 6 minutes. And as the data size increases, you will notice that this difference between sklearn and COML becomes even bigger. So rapids becomes essential when you are experiencing, I would say, even more than 15 to 20,000 rows. Like, it would be a shame not to use it just because it's exactly the same as sklearn and it performs much, much, much faster. Yeah, and this was my presentation. I'm super happy that you've been here. If you have any questions, you can reach out today or on LinkedIn or anything. And thank you so much for listening.
Thank you, Andrada. I actually have to admit, I saw you doing this QPI, QDF on one of your notebooks on Kaggle, on some Kaggle competition. And I was like, oh, wait, what is this? I actually tried to figure it out myself, but I kind of lost it. And now I finally understand why it is so useful. So for me, it was quite useful, this presentation, but I think that many others agree. So I realized that you guys did not saw our slides, so maybe I can share it now, because our next speaker is one of our co-founders from our chapter in Bucharest. Is Ana Maria Niculescu. She is a data scientist at Numeract. She's leading a small but ambitious team. Interesting fact, she graduated 2 years ago from a master exactly in France, master in data science, of course. A challenge she faces quite often is scaling data products in production while keeping the focus on data science. She's an active member in our R-Lady community in Bucharest, since she uses R in her daily work. So today she will teach us how to deploy R in production on the Amazon Web Service platform. The floor is yours, Anna.
Hello, everyone. Bonjour. And thank you very much for the invitation. Can you see my screen first and foremost?
Yeah, I'm confirming.
It's for now? All right. So as Claudia said, I'm going to talk about solutions for running R on Amazon, and more specifically on Amazon Lambda, on AWS Lambda. A little bit about us. We are a small team. As Claudia said, we have data science. We take data science projects, and we also work on open source projects when we find the time to do so. Our main technologies, the technologies we work most with, are SQL, R, Python, Docker, and last but not least, AWS. And for the project I'm going to present, we collaborated to it, and it is actually open source. You can find it on GitHub. So first of all, I'm going to start with presenting the problem that we faced and what we needed in order to solve it. I'm going to talk a little bit about APIs, about AWS, and more specifically about running R on Amazon Lambda, and about the solutions we found. And I'm going to wrap all this discussion in the conclusions in the end. So what was our motivation to start running Amazon on AWS? Well, deploying R in production was not very easy for us, but it was a really good problem to have. That meant that our project scaled. So the client was happy with the code, and we needed to make it accessible for other applications also. So how did we start it? We had a nice shiny dashboard for data visualization as well as model validation. But in time, features to the shiny dashboard added. Also in the backend, that shiny app was also reading the data, was performing some data cleaning, was computing features, and was building prediction models that were displayed in the end in the dashboard. But the client needed just the piece of code that was performing the calculation process. And he needed it to access it outside and independent from the Shiny app, from our dashboard. So what to do? Because the application the client needed the calculation process for was not R. The programming language in which the application was written was not R. So writing the code in another programming language, it was a no-no. It wouldn't have been efficient. We would have lost much more time than we needed to. And certain algorithms may not be available in other programming languages, even Python, as well as certain algorithms may be available in other programming languages, they may not render the same results as in R, and we wanted to be consistent with our results. It was really important. So what was the answer to our problems? The APIs. The APIs are actually, APIs in general, are an interface between different software products. And they would help us really to modularize the application we had. It is also programming language independent. It is a common concept, and most programmers know how to work with it and know how to make an API request from another programming language. And it is a common data language, meaning it returns our calculation results in a JSON format that could later be used by others. So can we serve API requests from R? Well, not directly, because R is not a web server, but we needed a wrapper around R so that R could serve the results to our client. What were the candidate approaches? First of all, we thought about Plumber and OpenCPU, but then we got to R, running R on AWS Lambda, actually wrapping R in a function as a service, which is AWS Lambda. So let's wrap up our requirements. What our app task engine should do? It should get a request ID from the client. It should read the data from the DB based on that ID. It should process the data from 5-20 seconds and return the results for the client to use them further. So how could we run this code in production? Because we needed it to be available as long as the client needed it, but turns out the demand was uncertain and irregular. And we needed something to trigger those calculations without us being actually there. Another problem was that our code, the part of the calculation process, was still in development. So we could not afford to always redeploy the code by hand each time we changed something in the calculation, and each time we calculated new features, for example. So we turn to Amazon Web Services. That's a little bit of an introduction slide so that you know my vocabulary. Amazon Web Services is a collection of pay-as-you-go cloud services. It has a lot of products, but the ones we actually needed were these ones, the abbreviation I'm showing to you. IAM stands for Identity and Access Management. It's the service that ensure security in Amazon. We needed a VPC. It's a virtual network so that our code is not out in the wild. An EC2, a virtual machine, actually. When you see EC2, you think about a virtual machine on which we deployed the code. The API gateway, the S3, which was the storage, we put there our code. And the Lambda function, which is the serverless application service that AWS offers. In detail, what's Lambda? What's this thing? Well, it's basically a container. It's basically a small virtual machine, if you want it to be small, that it's launched and runs code just as long as it needs to run, and it is it's only launched when it's explicitly triggered by an event. And in our case, the event that triggered Lambda was the API. It helps you build apps very fast while minimizing infrastructure maintenance. It lets you keep the focus on what's important. We are data scientists and we do not want to do DevOps tasks. And you pay only for what you use. And as I said earlier, remember, it was an irregular demand, meaning maybe today I had like 3, 4, 10, 1,000 requests, and tomorrow I won't have anything. And I don't want a server to be up 24/7 and waste resources. And it is also horizontally scalable. How to run on Lambda? We got to the main point of the discussion. Well, turns out it is not as intuitive to directly run R on AWS Lambda, because when you go to the cloud interface of AWS and you go to Lambda, you will actually notice that R is not there. You see Java, Node, Python, Ruby, different flavors of them, but no R. Fortunately, there is a way to run R on AWS Lambda, and that is through custom runtimes. So our runtime is defined by us, and that we plug into the Lambda function and use it to run code in any programming language we want, including R. So our approach was to not reinvent the wheel. So we used a base R custom runtime provided by Backdata, but we also needed some other packages, especially the ones from Tidyverse, as well as Carrot. And what we did in order to ensure that we had all those other packages besides the base R runtime was to create like a sandbox for the application to run. It's a zip file that contains the libraries, the R libraries, the additional R libraries we wanted, and pass them to the Lambda function, sorry. Other approaches would have been to use the package rpy2 to call R code from Python, which we actually did at the beginning because we had this problem before custom environments appeared. And another solution would have been Lambda R, it's an R package that triggers a Lambda function from R. But we stuck to Lambda with custom runtime environments. That's the main architecture. It looks simple. The user makes a request to the API gateway, and the API gateway triggers the Lambda function, which loads the R code stored on S3 and processes the data, performs the calculation, and comes back to the client with a JSON response. Actually, I needed here another arrow in the direction of the client. Well, it looks simple, but you don't want to click through the entire interface of Amazon to do that every time you want to redeploy the code, especially when you have multiple releases. And let's not forget about security, because that's an important aspect too. In order to ensure access to the API in a secure way, we needed to validate a token the client needed to have in order to access the calculation process. And in order to do that, I know that's a big picture. I'm just going to concentrate on this one. This right here, we needed to write another Lambda function that was able to validate the request that from the client. So the infrastructure was pretty big. It involved many actors on the AWS side, and we needed to synchronize them in a fast way. We didn't want to click through the interface all the time. So what we did was to write a series of shell scripts, not R code, that put everything in place in order to run R on AWS Lambda. The main tasks, let's say, that these scripts would do is to deploy R function, the R function on AWS Lambda and configure the access to AWS Lambda through the API gateway. In more detail, the scripts use your settings, your credentials to connect to AWS, to create a virtual private cloud, to create the storage buckets and authorization policies. It installs and compiles your R packages, creates the zip file that you need to load inside AWS Lambda, creates the Lambda functions and creates the API and configures it in a secure way. And the scripts can be actually be run from any platform, even though they are shell scripts, which also use Amazon command line interface. It's the command line, it's a tool offered by Amazon to run commands for AWS through command line. But they are all run through Git Bash. So if you use Git on your computer and you have Windows, you know that you can click, you can find Git Bash and you can run Unix commands in there. So it's pretty versatile. That's an example of a really, really small, it's just an illustration of function that can run on Lambda. But imagine that you have multiple tasks and this is just the main function that you send. The function gets a request ID. Here you can have perform any operations you want. Maybe you want to normalize your features. Maybe you want to perform imputations. Maybe you want to make some predictions, whatever you want. You can do it in R. And then you wrap up your results in a JSON format and you send it back. You return it actually to the API. From command line, the situation looks like this. So this is the part in which the settings have been loaded from your computer, and then it's making some checkups before starting the entire infrastructure. The API result looks like this. As I said, it's a JSON. This is just an example. And in the end, you get the entire infrastructure loaded in AWS without you needing to do anything more than just creating the minimal settings and passing them to the scripts and then launching the scripts. As I said earlier, the scripts use AWS command line interface, so you don't need to click through the Amazon console anymore. You pay as you go, so you don't have to have the server up without any requests. It is really fast to deployment and after each release, so you keep your focus on what's important for you. You don't have to click. And it is easy to adapt. Those scripts are actually really easy to adapt to automatically deploy other code written in R or JavaScript, for example. There are also some limitations. This is why Lambda was a really good answer for our problem, because we had small tasks. Lambda has, the purpose of Lambda is actually to run for a very limited amount of time and then to shut down. So you imagine that if you have something that runs from, I don't know, for the entire night, it won't work. But for tasks that can be performed rapidly, and as well as irregular that are irregular in their demand, it's very, very nice. Finally, as I said earlier, there's a fine line between where the data science stops and where data engineering or even DevOps begins. We wanted to focus on our tasks. So we found a custom solution for our problems. AWS was great for our needs, Lambda too, especially since it's more flexible lately. Scripts still run in production, so the client is happy. And it's really worth automating something. Maybe if it takes you a while to learn about all the, I don't know, the small details of Bash and Amazon command line, but this advice applies to any other tasks. It's really worth automating something in order to be able to focus on what's more important for you later. That was it. Thank you. You can find me on LinkedIn, via mail, on GitHub, and I'm really looking forward to your questions after Denisa's presentation.
Yeah, thank you very much. It was very interesting. I didn't know that it would be actually possible. It looks like you've been through a lot of trouble, so thank you for going first. And now it will be easier for us. For the next presentation, we will be welcoming Denisa. And Denisa Banulescu, she will be talking about how you can use data science for financial fraud detection. Denisa, if you would enter, if you can. Yeah. And in the meantime, maybe if you have a question, either for Ana Maria or Andrada, we can take them now because it looks like Denisa may have.
I have just to share my screen. Okay.
Oh, okay, you're here. Cool. Okay, so the floor is yours now. Thank you.
It's okay. Can you see my screen?
Yeah, we see you hold desktop, so maybe you want to.
Yeah, of course.
Focus on the slides.
Of course. Here. Okay.
Cool. Yeah.
It's okay. Can you see my slides?
Yeah,
now?
we can have the borders, but it's okay. The slides are big enough. Yeah.
I can hide them. Okay. Okay.
Yes, perfect.
I think that is it's better now.
Yeah.
Okay. Hello, everyone. Let me first thank you for the invitation and for giving me the opportunity to present a part of my current research. It is an honor for me to represent Paris today and to present my research in this joint session with my colleagues from Bucharest. So my presentation today will be an academic one, if you want, and will be focused on the use of machine learning and data science methods for the detection and the prevention of financial fraud. Before getting to the heart of the topic, please let me introduce myself and explain briefly my background. So since 2015, I'm an associate professor at the University of Orléans, and before it, I was a Max Weber Fellow at the European University Institute in Florence for 1 year. In 2014, I got my PhD in economics and more specifically in financial econometrics from Maastricht University and the University of Orléans. Concerning my research interest, as you could observe from my background, I'm mainly an econometrician, focusing on financial econometrics topics such as volatility modeling, systemic risk, backtesting, and fraud detection and anti-money laundering. So this last topic, which is really very interesting and complex, is at the crossroad of economics, econometrics, machine learning and law, reason for which for this part of my research I have to use both econometrics and the machine learning tools. So my presentation today is organized as following. The first section is devoted to a brief comparison between econometrics and machine learning, the general aspects of fraud, some of the main challenges identified in the fraud detection modeling and the solutions proposed in the literature. And in the last section, I illustrate the topic via two case studies. So let's see first which are the main differences and the common points of econometrics and machine learning, and how can they come into symbiosis, if you want. Econometrics is a discipline that appeared in the 1930s, and say that in the pragmatic way. Econometrics is a very good mix of economic theory, mathematics, and statistics. As for machine learning, this discipline was born at the end of the 50s, and to simplify, it can be seen as a good mix of mathematics and computer science. But what is important to know is that these two disciplines have a common purpose, which is the one to create an explanatory and or predictive model for a variable of interest using explanatory variables or predictors. However, the two disciplines developed in parallel by creating two very distinct cultures, and now in the era of big data, it becomes essential for us, for the econometricians, to understand the two cultures, to understand what opposes them, and the elements bringing them together in order to appropriate the tools of artificial intelligence and integrate them in the economic models. So let's see which are the main differences and similarities. So machine learning's first or primary strength, it's adaptability. You can find it in marketing, medicine, fraud detection, and so on. And this simply because it is data-driven, and you don't need a specific theoretical distributional assumptions in order to apply machine learning. Its second advantage is its accuracy compared to that of the classical econometric methods. The machine learning accuracy is almost always at the top of the ranking. Of course, it presents also significant drawbacks, the first being that the algorithms become more and more complex and hence impossible for a human being to interpret them. And the second drawback is its tendency of overfitting. Let's turn now to econometrics. The main advantages are concentrated around the high interpretability of the method, which can be for some industries even more important than the predictions themselves. Another advantage is the fact that we can easily perform statistical testing, and that the analysis is based on the concept of causality, which is richer than the concept of correlation generally used in the context of machine learning. The main drawbacks are that econometrics is theory-driven and mostly parametric, of course, and the forecasts given by econometric methods are less accurate than those obtained by machine learning. Nevertheless, as you can observe, as you can see, the qualities of one seem to compensate for the shortcomings of the other. So it becomes interesting nowadays to combine the two disciplines. So these methods tend to no longer be competitive, but rather complementary. And of course, the number of bridges between econometrics and machine learning continues to grow, as cited by Hal Varian, professor of economics at the University of Michigan and the chief economist at Google. Here are a of areas where there would be opportunities for nice collaboration between econometrics and machine learning, and I think that that fraud detection is one of them. Okay, why is fraud detection important? Here you have the main concluding remarks of a conference organized by Finance Innovation in Paris just before the pandemic period, and other key figures on fraud. And as you can see, the fraud detection is a hot topic nowadays with a huge global impact. Okay, so to define fraud for my research, I prefer using the definition given by Bart Bassens and his co-authors, who say that fraud is an uncommon, well-considered, imperceptibly concealed, time-evolving, and often so carefully organized crime, which appears in many types of forms. Here, so as you can see from this definition, it puts together the main characteristics of fraud, which can also be considered as the main challenges for the modeling process. Here you have just some of the forms taken by financial fraud. So we can talk about credit card fraud, insurance fraud, money laundering, and so on. So let's see now which are the main challenges and the solutions proposed in the literature for the fraud detection process. And for today's presentation, I only selected 4 of them. Okay, so first, fraud is a complex, time-evolving, and intentional phenomenon. As we saw, financial fraud can take a wide variety of forms, and even though their characteristics are the same and the final objective consists in detecting fraud cases, the solution to each problem is rather attention domain specific. Another problem is that the fraudster's behavior is time evolving, meaning that fraudsters learn from their mistakes and correct them very fast. Additionally, fraud is intentional. It is a deliberated action, which means that the IID assumption generally used in statistics is likely to be violated, since fraudsters often collaborate to create complex fraudulent networks, right? Secondly, fraud is a rare event. Generally, the data sets used for detection are huge, but highly imbalanced. So most of the time with a fraud ratio that is less than 1%. So there is a huge number of legitimate transactions and only a few fraudulent transactions to learn from, which makes the detection process even more complicated. Third, fraud detection models are difficult to evaluate. So let's take the example of prevention models, which are designed to detect the fraud before it occurs. If a prevention model is performant, so no fraudulent transactions will be observed ex post, right? But if there is no fraudulent transaction ex post, it may be also the result of luck and not of the model. So in this case, nothing guarantees that no fraud will occur in the future, reason for which a specific attention is, of course, required on the validation of fraud detection models. And last challenge, most of fraud detection models are difficult to interpret, and I'll come back to this and elaborate more on this issue in a few minutes. So let's see now which are the main solutions to overcome these challenges, and focus first on the main tools used nowadays to fight fraud. Most of studies employ nowadays standard econometric methods for fraud detection. For instance, we have a logistic regression methods and their extensions, of course, that are commonly used to describe data and to explain and or predict financial fraud. But recently, traditional models have been replaced by data mining models, and machine learning methods emerged to solve fraud detection issues. The three main types of machine learning methods that are mostly used for fraud detection process are the unsupervised, supervised, and social network learning methods. Okay. Which are now the solutions to deal with the imbalanced data set? The topic of imbalanced learning has been widely discussed in the last 2 decades, and different methods have been proposed. We have the data sampling, where the training data set is modified in such a way to produce a more balanced class distribution. Then we have the algorithm modification, where this time the based learning methods are modified to deal with the imbalance issue, and the cost-sensitive learning, which considers higher cost for the misclassification of the minority class instances with respect to the majority class instances. And to the best of our knowledge, unfortunately, this issue is minimally treated and corrected in the context of fraud detection. And for my research, I'm using, so I'm correcting the data for this issue, and I'm using the first family of methods proposed in the literature, which are the data sampling methods, and more specifically. So I'm using undersampling methods, oversampling methods, and the hybrid methods. Here you have an example of a transformation of the data set using the oversampling method called SMOTI. And on the left side, so you have the imbalanced data set with only 1% of fraudulent cases, and on the right side, okay, you have the transformed data set using the SMOTI method, and now with 20% of fraudulent cases that were created. Next, for the evaluation of fraud detection models, I investigate 3 key points. So first, the performance metrics to be used based on the main characteristics of the fraud detection. Do not forget that our data sets are highly imbalanced, and most of standard metrics are no more appropriate because they are insensitive to skewed distributions and can lead to suboptimal classification models. Let's discuss a bit the accuracy paradox, for instance. You might have heard about it. Consider the example of a data set with only 1% of fraud cases. So in this case, if a model classifies all the individuals in the majority class, we still obtain a very good classification of 99%, which is excellent at first glance, but extremely bad in the context, in our context in which all our fraud cases were misclassified. So this is why selecting proper evaluation metrics play a key role in this context. A second decision focuses on the statistical test that can be used for the comparison of the performances of different techniques. And importantly, in the context of fraud detection, there are also some other criteria that are to be taken into account when evaluating a model, such as the interpretability of the model, the operational efficiency, the economic cost, and the adequation with regulatory compliance. As you know, fraud detection model should be in line and comply with all applicable regulation and legislation. As for the interpretation, of the models, as Ribeiro state, if the users do not trust a model, they will not use it. So you can see that the interpretability is also an important element for the management to trust the model and to design fraud prevention strategies. And of course, several different methods have been proposed in the literature. But to what extent do we need our fraud detection models to be interpretable? Obviously, in the case of fraud, there is a clear trade-off between the predictive performance of fraud detection models and their interpretability, and the types of fraud requiring more interpretability are those that are more regulated by a supervisory authority. For instance, I can give the example of money laundering, but for all others, we can favor the precision task or the accuracy task. Additionally, regarding the customers, the firm has no obligation to explain to a client why a transaction was red flagged, because the fraud detection model should remain opaque, right, for the customers and for fraudsters in general. Okay. Before going to the empirical part, I'd like to add that practitioners have another very important problem that is related to the human resources available to treat red flags. So suppose that we have a great model with very good predictive abilities that perform very well. At the end of the day, only a limited number of alerts can be treated because of a limited human staff involved. So this means that many cases of fraud may go unnoticed even in the presence of very good tools. So I present you now very briefly two case studies, two case studies based on different types of fraud, the household fraud and the social fraud. And the idea here is to show how different types of fraud require different modeling strategies, different tools, and different approaches. And as you see, we use mainly machine learning tools for the detection of household insurance fraud and pure econometric tools to deal with the social fraud. Let's start with the insurance fraud detection, which reflects typically external fraud such as automobile, household, healthcare, and crop insurance fraud. And for this study, I focus on the household insurance fraud. So in this study, we take into account most of the challenges presented previously and propose an empirical analysis based on real data. So we have a database of about 46,000 house claims for the period of 2013 to 2017 from a French insurance company, and only 0.76% of the claims that are fraudulent, which means that here we deal with a high imbalance data set. So we propose a clean methodological framework based on technical tools such as the logistic lasso, random forest, and ESG Post, and to deal with the problem of imbalanced data sets, we use three oversampling methods, namely the random oversampling, SMOTI, and ADASIN. And the evaluation of the model's performances is done here based on metrics such as AUC ROC, AUC PR, precision recall, Breyer score, and so on. So for the analysis, we started the analysis by a standard treatment of the data and perform data processing, the feature engineering and variable selection. And then we continued with the model training and the evaluation of our model. So a stratified splitting on the data set was performed, of course, in order to obtain the training and validation data set and the test or the evaluation data set. The models were, of course, trained and validated on the first subset of data based on a k-fold cross-validation procedure, and tested then or evaluated then on the second data set. So this exercise was done both on data, on raw data, and on data corrected for the imbalance issue. Next, for the interpretation of our results, we use the standard SHAP value, and we identified at both global and individual levels the features driving up and down the probability of fraud. Unfortunately, for confidentiality reasons, I cannot present all the results to you today. Okay, the second case study focuses on the social fraud detection, and here we are mainly using econometric methods. So for this, we are in contact with a French mutual organization which collects data systematically from their taxpayers, organizes regular controls on a subsample of their taxpayers, and manages fraud detection system to identify those who do not pay. Okay, so let's see which are the agents that are involved. So our objective here is to estimate the tax shortfall, okay? And this tax shortfall is defined as the potential sum of the adjustments, okay, that could have been imposed on companies having defrauded, or if they have been effectively audited, or else they were not in reality. Okay, so here we have two types of agents. We have the firms or the taxpayers and the control body, and each of them can take decisions. Which means that the firms or the taxpayers so can decide whether to fraud or not, and the control body in this case decides which firm to control and not to control or to audit. Okay, so what is important here is that the two decisions are neither sequential nor conditional, which means that the fact of being audited does not condition in any way the fact of defrauding, and vice versa. Okay, so However, the decisions in this case are linked in the sense that if the control body, of course, fulfills its mission effectively, right? One should observe a greater probability of control for the companies being audited than with, of course, in relation with the companies having the highest probability of fraud. Okay, so here you have an example of an individual for which we have to estimate this tax shortfall. Here you have a guy who made fraud, but who hasn't been audited by the control body. Okay. The problem here is quite complex because we have to deal with a double bias. So as we only observe the amount of fraud only for firms that were audited and made fraud, and the tax evasion or the tax shortfall should be computed for the firms that have not been audited. So to solve this problem and take into account this double bias, we adopted here a purely econometric and parametric approach and translated the behavior of the agents by this trivariate system of equations. So with two binary variables, so for the control decision and for the fraud decision, and a continuous variable for the tax shortfall. And the estimation here was done by, as I already said, by a purely econometric method, which is the maximum likelihood. Again, unfortunately, I cannot show numerical results, but I hope I have convinced you on the value of the importance of using econometric and machine learning tools. So either in symbiosis or independently in the field of fraud detection. So thank you very much for your attention.
Thank you, Denisa. Thank you very much. It is very, very interesting. I hope we'll have question. We'll can then go to the question actually for other presentation. We had one already for Andrada, and she answered in the chat already, so that's cool. If you have a question which feels a little bit too long to write in the chat, you can just raise your hand and unmute yourself to ask a question. And don't, of course, don't be shy. Maybe, actually, I have a question, so maybe I can start so people can write their question down if they want to have some time. You talked about the fact that it was difficult to build a data set, it was unbalanced. And indeed, well, to train a detection model, you need to have positive examples. So how do you find them in the big amount of data you might have if you don't have a detection model already to help you spot them? And actually the sub-question is, don't you might have bias because you might control people who you might think should fraud because, I don't know, maybe they're poor or well, any kind of bias in that kind of data set?
Yeah, very interesting questions. So for the question related to the imbalanced data set, as you saw, we only have 0.76% of fraud or fraudulent cases, which means that we are in the case of a highly imbalanced data set. And in this case, of course, our models will perform badly because they, in the case of skewed distribution, okay, they have the tendency to classify all the observations in the majority class. Okay, and in this case, we have three solutions presented. So first, we treat the database. We modify our database in order to get it to obtain a more balanced database in terms of the class distribution, of course. The second solution is to modify the algorithm used for the by the method, and here we have several solutions that were proposed in the literature, and the last solution, which is the cost-sensitive learning, where we impose where we have higher cost for the minority misclassification. And in our case, so we use the first family of methods where we touch. So we modify the database in the sense that here, for instance, I'm using oversampling methods, which means that in this case, I create synthetic observations for the minority class. But what is important to know is that, wait, just 1 second. What is important to know is that, I don't know if you can see my screen.
Yeah,
yeah, the resampling. The resampling here, you see, the resampling is done only on the training and the first subset of data, so the training and the validation data set, and not on the evaluation data set. Okay, so like this, we can keep the representativity of the skewness in the class distribution, right? Other adjustments to be used is to modify, is to adjust also the probability of fraud, because here you have a probability of fraud that is computed, and knowing that you evaluate your model on the evaluation, so on the second data set, in this case you can also adjust your there are some methods to adjust these probabilities. Yeah. Okay, and for the second question, the same. So here, of course, we talk about double bias, because as you said, we have to here. So we have to estimate the tax shortfall. So for the individuals who made fraud, but who were not audited, verified, checked, if you want. So in this case, is by the means of this econometric specification that we take into account this double bias, selection bias.
Okay, thank you. That's very interesting.
Welcome.
Yeah. And we have questions for you in the chat. The first one is, could you please talk a little bit about Brier score and why are you using it? Okay, so Brier score, and I go back to the performance metrics, sorry. I just explained you the accuracy paradox, which means that when you deal with the highly imbalanced data set, you cannot use anymore the standard metrics proposed in the literature. And here, so you have to use metrics that are appropriate for this proper metrics, so appropriate to deal with this imbalanced issue. And Brier score is a probabilistic metric. Is it so in this category in the performance metrics? Brier score is a probabilistic metric which can deal with the imbalanced data set issue. Okay, I think it answers the question. Maybe Diana, if it doesn't, please just write something new in the chat. We have another question as you mentioned, there is a high possibility for the actual label to be wrong. How can you assess the validity of the labels in the dataset?
Yeah, the labels, right. Another very interesting problem. Of course, today I only presented 4 main challenges, but the list is very long. We have data availability and also the target. Here, what is important to know is that we have 2 types of methods. We have the detection methods and the prevention methods. So for the prevention methods, we don't need the historical labeled data, but for the detection methods, effectively we need these labeled data. So, for instance, a binary variable who says that the transaction is a fraud or not. And of course, the label, the target indicator is not noise-free because we are not fully sure that a transaction or a claim or a company is fraudulent. And in this case, is in the model risk that we have to take this into account. I don't have a magical solution, unfortunately.
Thank you very much. Indeed, I think it will always be the problem when do you have the true in the end. We have another question, this time for Andrada. That question is, in your opinions, and since Rapids is restricted for NVIDIA GPU and has other bounds, how easy should be deploy that? How easy should be to deploy a model that uses Rapids in the near future?
Okay, so that's a very good question. I am not very experienced and I'm not comfortable to talk about something that I don't really know. But what I can tell you is that there are, I don't know how familiar is everybody with Kaggle, but there are lots of grandmasters there that are very skilled people and that are working for NVIDIA and on Rapids, whilst they are also working in big companies and deploying models. So what I would recommend you do is chat to them, meaning that you can go to Twitter, for example. I can drop some names here. You can go to Bojan Tunguz or Chris Deote. I will link them here. And you can message them because they will most probably answer and you can find out what's their opinion. I'm not very sure how to answer this, unfortunately.
Thank you very much. Yeah. I don't know if we have other questions. If anyone has some, it's still possible to ask. Is anything coming to somebody's mind?
So I have a question for Anna and one for Andrada. For Anna, I have a question. Why maybe I wasn't fully get that part. Why did you prefer to use an R custom approach with an R script rather to the library for the AVC? And for Andrada, I was just curious if you use Rapids for Kaggle, it helped you in which sense? You showed us that you reduce the time which was wow. I mean, from 6 minutes to 20 seconds, it's quite a difference. And I was curious in your experience with the Kaggle platform, how you felt the use of Rapids. So these are my 2 questions for now. Thank you.
Should I start? All right. So why did I choose this custom? Did we choose actually this custom scripts with AWS Lambda as opposed to Plumber, for example, or Lambda R, the package in R. Plumber is actually another package in R. It's because the other solutions actually meant that we had a server running 24/7, but we had irregular demand, meaning leaving a server up for 24/7 just to wait for the client to make a request was costly. And why waste money when you could use serverless applications, as that's what happens with Lambda. When a mini server, a serverless, actually a container is launched just when you need it to launch and runs for as long as it needs to run in order to make your calculations, and then it stops. That's less costly, and that is why we chose this. Again, that was a solution for our problems because we had irregular demand, and we had tasks that were that didn't take so long to compute. So Lambda was optimal for us. That's why we chose it. Yeah.
Thanks.
Okay, so Rapids, and I know I've talked about the fact that it's very, very hard to install on your local machine. It's not as easy as pip install pandas, that's for sure. It's not that hard, but it's not as easy. But with the Kaggle environment, so it was a bit of a evolution there as well. When I first started and I used the first time Rapids on the competition I showed you earlier, it was somewhere in October. And at that time, Kaggle didn't have implemented the Rapid software libraries yet. So what you had to do is Chris, the one of the 2 people that I written in the chat, has created a data set with the latest 2 versions of Rapids. So you had to first kind of install them in your notebook on Kaggle, which would take around 1.5 to 2 minutes tops. And then you would be able to use Rapids. As I said, now Kaggle already has Rapids implemented within their ecosystem, I would say. And it's much, much easier. But I've been seeing more and more people, especially in big data and machine learning competitions, using, you don't see PD that reads CSV anymore. You see CUDF that reads CSV. So it's a natural progression towards it. And this is why I think maybe regarding the last question, there will be maybe some implementation in the future that will help Rapids be implemented in more complex projects. I think there still are, but I'm not very familiar with them.
Thank you. Thanks.
Okay, so thank you everyone for your question. I don't see any new one in the chat. So given the time, I think it's time to close this meetup. Thank you everyone for coming. Thank you to the speaker. There was one comment in the chat, high level presentation, completely agree. It's very great. I think I've learned a lot personally tonight, so thank you. And thank you also to the Bucharest meetup for this joint meetup. It was really fun to do with you.
Thank you very much.
Thank you very much.
Thank you everyone.
Thank you very much.
Bye.
Bye-bye.
Bye.
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 Goodbye.